All right, guys. As you can probably tell, I'm not there today. Also, just so you know, I'm heading back from my vacation, and I will be here on Wednesday. But in the meantime, we have, if you don't realize this, we got this week, next week, and then exams. So things are going to be moving rather quickly. Our last little unit we're going to cover here is probably one of the easier ones we'll do. And if you've done vectors already, then you may already be familiar with some of this material. But it's really taking some of the concepts we've learned already, minus the trig identities. I mean, using the unit circle and stuff is going to be a part of it, and special right triangles could be a part of it. So all those things that hopefully we're masters at by now, we're going to be applying as we go through vectors. So if you've done vectors, like I said, this will be a little bit of review for you. So if you already printed this out, that's great. You don't have to, obviously, but a lot of the things that I'm going to start off with involve no writing whatsoever. I'm just kind of talking about what's already here. If you've read this and understand it, you can kind of skip ahead till I actually start working some examples out. That's really up to you, but you do need to understand this material. So starting off with what a vector is. Now, what a vector is not is array. This is what a vector looks like, just a plain old vector without it being written in the XY plane. It looks like array, but the thing is it is a line segment, and the arrow doesn't mean it goes forever like it does for array. It means what direction it's heading. So I'm going from A to B. So again, vectors have to have a direction. And really what it represents a force. And, I'm getting ahead of myself because that talks about magnitude, but that force has to be pushed in a direction. I like to go over that stuff in class and talk about force, but I'm not there, so we just kind of make do with what we got. So the direction tells me, like if I was pushing a chair, what direction I'm pushing that chair in. As you write the vector out, if you are writing it out like the way I have it, which you actually will not see very often, vector AB, A is your initial point, your starting point, and B is the terminal point, or where you are pushing it, the direction. But as you will see, as I move this out, it's usually just referred to as like by a name. And the most common name is V, vector V, because vectors start with the letter V. So anyway, that's what a vector is for the most part. Now it does have a length, and as I was talking about it, it represents a directed force. So the force is denoted by what's called its magnitude, and this magnitude is the length of the vector, and that length is going to denote a force. The bigger or longer the vector, the more force that's being applied to it. The shorter the vector, the less force that's being applied. And I will kind of show you why it is what it is here in a second, but the notation for magnitude is going to be this absolute value symbol. That is an absolute value, and there's a reason why we use that, and you'll get to that. I'll get to that in this video. So that's what a vector is. Again, as I said, is a directed force. Is probably the best way to summarize everything. So you need to make sure you have direction, and you have to have a specific length to represent the magnitude or the force of the object. Okay? Now, what we need to do, this is a math class, we need to apply math to these vectors. So you know what a vector is, great, but we need to apply math to it, and obviously, and I'm saving all the applications for when I get here. There's a lot of applications for vectors, and those applications will get taught starting Wednesday, or Thursday, depending on when I see you. So be ready for that. But we need to know how to do all the math that is required of us. So starting with addition of vectors, addition and subtraction. These operations are the easiest operations I can possibly think of. But first off, if you have two vectors, this is what's happening visually with the addition of two vectors. So if I have one vector, let's say that's vector, U, and I have vector V, which is the second vector, what we get is we get a new vector, and it actually looks like this. So as I go over all these rules, this vector is going to be vectors U plus V. So that's what's happening visually, but really when you're adding vectors, you just plain add them, and I'll get to the details of that in just a minute. You'll see it in the notes if you already have it printed out. But that's what's really happening is when you add two vectors, the vector is going to get longer. I mean, that's what's going to happen. And it also, notice, it affects the direction. All those things are going to be affected, and you're going to get a brand new vector with all those forces being applied. And again, it's very simple to do. Next up, with multiplication of vectors. Now, when you multiply vectors, you're not changing the direction. So if I wanted to do, say, 2v, if this is my vector v right here, and I want to do 2v, I'm just going to get a longer vector. That's all that's happening. So this would be 2v. And I'm obviously just kind of guesstimating that. But the big key on this here is the direction. I need to make this really actually match up here. But if I was doing this the right way, and I'll try to do it the right way, all that's really happening is you're making this vector twice as long. So that's, again, all that's happening here. I'll get that to match up. So there's 2v. And again, the direction hasn't changed. Same thing if I did, 1/2 v. Again, here's 1/2 v. I'm trying to do that better. There we go. So there's 1/2 v. And again, if I wanted to move that, I could. It's just kind of hard to do it right there, so I'll kind of write it next to it. Wasn't really thinking ahead there at all. But this is going to be your 1/2 v. And again, I can do a bunch of these, but you kind of get the point, hopefully. It doesn't change the direction of the vector, it just changes its magnitude. And again, those are the only two things you can really manipulate in a vector, is its direction and its magnitude. What way it's facing and how long it is. So that's multiplication, and technically a little bit of division if you think about it, because 1/2 is the same as divided by 2. Before, and one thing, I haven't really brought up all the rules for addition, subtraction, multiplication, division of vectors, because we need to bring up component vectors, which is going to make the math a heck of a lot easier to do. So this is what you're going to see the most of as we go through everything, and that's going to be component vectors. So component vectors are written in this form. And notice in this component vector form, we don't have points. I mean, it looks like it's a point, but pay attention to the fact that what we normally have as parentheses are actually sharp corners. And the fact that I don't have parentheses there represents that this is not a point, it's a vector, and it's in a component form. Although AB does kind of represent a point in a way, but it's the terminal point of the vector. So anyway, some parts of this, so you understand how this works. I'm going to draw a picture next to it over here. But this vector is, if it's in component form, again, our initial point typically when we do these is going to be 0, 0. And A is going to represent your horizontal component, and B is going to represent your vertical component. And again, the rule isn't necessarily that a component vector has to have this initial point, but when we do the math with component vectors, that's where you want it. So I literally just state, hey, when we do a component vector, make sure that initial point's at 0, 0. Just put it there. And then we have our horizontal vertical components, which are like your x, y values. And then we can find a magnitude as well, which I'm going to get to that in just a second. So let's get a visual for this so you know what the heck I'm talking about. So let's say you have your xy plane. So there's your x-axis and your y-axis. So when you write a vector in the xy plane, in component form, I'm going to start that vector at 0, 0. So as you set this up, it's going to create, and you'll see a lot of these now, it's a little right triangle, where A is going to represent the horizontal component of that vector. B is going to represent the vertical component of that vector. So to get to this terminal point, I have to go right A and up B. And as I said, that's where I said this kind of represents a point. It represents your terminal point. But this is, again, going to be vector V. Now, if I want to get my three lengths, there's A, there's B. Those are lengths. This length is going to be the magnitude of that vector. And the magnitude, again, is denoted with an absolute value symbol. And by the way, as I write up this is the component form AB. If I took that component form and put it in a graph, that's what it looks like. Okay, and again, your terminal point is at the point AB. These do kind of match up. So anyway, to talk about why we use absolute value to represent magnitude. Well, magnitude is represented as an absolute value because absolute value is the length or distance, I should say, that a number is away from 0. For example, if you're on a number line, and this is 0, and I want you to find the absolute value of -2, you would say that's equal to +2, but here's why. The distance from -2 to 0, the distance is 2. That's how far away it is. So as soon as you get into an xy plane, we're now in 2 dimensions. So I'm going to take a point AB, and I want to find its absolute value. Well, what I'm trying to do is find its distance away from 0. In this case, 0, 0. How do you find this distance? You use the distance formula or Pythagorean theorem. So that's where this really comes from. That's why we use absolute value, because it is an absolute value. And that's why magnitude is represented by that formula, which is basically either depending on what you want to call it, your distance formula or Pythagorean theorem. Whatever like I said, you want to call that, it's really up to you. But it kind of works like this. You know, we have a squared plus b squared equals c squared. C squared is your hypotenuse. You square root both sides, and you have the square root of a squared plus b squared, and that equals, again, your hypotenuse. So what's your hypotenuse? It's the absolute value, or magnitude, I should say, of the vector. So that's where that magnitude formula comes from. So that's kind of trying to give you a visual here. Okay, so once we have all that, now let's just kind of do just some basic manipulations with this. We need to be able to do the math. Again, this is a math class. You know, it's nice to understand all these concepts, but we have to be able to, again, do some math here. So here I'm going to graph, and then we're going to find the magnitude of these vectors. So let's do the first one here. And this one is 2, -3. So I'm going to, again, graph my xy plane. And I'm going to go right 2 and down 3. I'm going to plot that point. So if I want to write this vector, I'm starting it at 0, 0. And there's the vector. Now, I want to graph it, which I just did. This is vector W. But I also want to find, get up there, the magnitude of it. So find the magnitude, again, that's where you set up the right triangle. And again, I'm wanting to find the hypotenuse. Remember, I'm going right 2, and I'm going down 3. So I'm just going to do my Pythagorean theorem. So you can write it out as the entire Pythagorean theorem or know the formula, which is the square root of a squared plus b squared. So I'm going to go 2 squared plus -3 squared. That's the square root of a squared plus b squared, or as I always like to call it, basically Pythagorean theorem. So that's your magnitude formula. So this is going to be the square root of 4 plus 9, which is the square root of 13. So there's your magnitude. So I have my graph, and I have my magnitude. Pretty straightforward, okay? So that's example A, and again, if I'm going to fast, pause it.